you very much. I'd like to take this opportunity to thank the organizers of this conference for having me here. It's been a deep pleasure and honor to be here. I'm going to talk about two different yet related topics that I've been working on in the past few years. They have to do with electron-driven processes in the chemical physics field and also biological physics. But before I even get into the talk itself, I'd like to tell you a little bit about basic timescales, the basic timescales involved in these processes. Here we have, if we talk about electron-driven processes first, so we imagine that those processes as collision of low-energy electrons with a target molecule. Very broadly speaking, we could divide those in two categories. We can talk about fast electron collisions, which take place in about a tenth of a femtosecond, and we can talk about russet electron collisions. Those are commensurate with a period of molecular vibration. They take approximately 10 femtoseconds to occur. When we talk about biological processes, for instance, fission, photosynthesis, molecular dynamic simulations, we're talking about nanoseconds. If instead we think about enzymatic and regulatory processes, then we're dealing with microseconds, and protein folding, structural reorganizations, for instance, take seconds, hours, sometimes even days. So we're talking about very different timescales here. And what can theory help us predict? Well, I'm going to try to show you throughout this talk that molecules can form temporary negative ion states by capturing a low-energy electron, and that these temporary anion states, which we call resonances, can enhance by several orders of magnitude the probability of certain reactions. It can also lead to distortions of polyatomic molecules that are necessary for a reaction to occur. I'm also going to show you how the mechanisms by which proteins bind metal ions, for instance, may lead to the disruption of strictures that are associated with disease. So let's talk about electronic collisions first. Why are we interested in them? Well, all around us, electronic collisions drive a multitude of common physical devices and chemical changes. And that's and why is this? Well, because the electronic collisions are uniquely effective in transferring energy into the electronic degrees of freedoms of atoms and molecules, and that's what makes certain phenomena, such as modern fluorescent lighting, so energy efficient nowadays, and it also makes possible the plasma etching of semiconductors. But what I'm personally more interested in has to do with radiation damage of live tissue, of biomolecules. And why is that? Because for a very long time, scientists believed that the main radiation damage was due to this primary ionizing event that went through tissue and therefore produced most of the damage. But it was very recently discovered experimentally that it is not that, but instead a large number of secondary electrons, which are low in energy, but can form these temporary negative states, these resonance states that will then lead to single and double strand breaks in DNA, for instance. So the mechanisms that the electron-driven processes hinge on the mechanisms by which electronic energy is transferred into nuclear motion to produce reactive species by excitation and or fragmentation. So let's talk about these resonances for a little bit more. How are they produced? Well, this picture you see here is it's a pictorial representation of a molecule. It's one of the many molecules I studied. This is called ethylene. And what you see here is a representation of its orbitals. Now, you see an empty orbital, sigma anti-bounding orbital there. A low-energy electron can get trapped, can get captured into that empty molecular orbital. That's what we call a shape resonance. Alternatively, this incident electron can excite electronic degrees of freedom of the target molecule and attach to it. That has another name. That's called Feshbach resonance. Well, I already talked about what timescales are involved in these resonances, and shape resonance, for instance, are commensurate with a period of molecular vibration. And what we will see is that the multidimensional nuclear dynamics and polyatomics lead to new effects. What you see here are a bunch of curves, a bunch of wiggly curves, which we call, in this field, we call cross-sections. And what these curves represent are a probability of a certain reaction to occur. What reaction are we talking about here? We're talking about a target molecule. In this particular case, it's nitric oxide, NO, and we have an electron colliding against nitric oxide and leaving that target molecule in different vibrationally excited states. So that's what these curves represent. Now, the motivation of this calculation was because we had originally two sets of experimental data, and there was a disagreement between this experimental data, and these calculations were good in the sense that it shed light onto which set of experimental results was more likely representing giving a more accurate representation of the physical process itself. But this is not what I found more interesting. This is what motivated the calculation, but what I found more interesting was the following. I decided I wanted to study dissociative attachment. What is dissociative attachment? It's another possible outcome. When we have this target molecule, we have a low energy electron scattering off it, forming this temporary negative state, this temporary anion state. One possibility is that the molecule then fragments into two pieces, and one of those fragments takes away the electron with it. So that's what's represented here in that equation up there. You see, and this fragment is taking away the electron with it. That's called dissociative attachment. Now, this particular reaction that's represented up there is something that the experimentalists measure, and the results of that measurement is negligible. And it's not surprising. But what I found surprising is that if instead of starting out the experiment with nitric oxide in its ground vibrational state, we started the experiment, well, the calculation in my case, with vibrationally excited nitric oxide, well, the cross-sections, this probability increases 1,000-fold. And so this was very exciting because it stimulated a new experiment at the Berkeley lab that is currently being performed. And so with time, we'll know, once they complete this experiment, whether this prediction led to something that they can now measure. Right? So this kind of prediction power is something that's always very engaging to people who do theory like myself. This is another aspect of these calculations. I started getting more and more curious about biological molecules, and I decided to study this very, very simple molecule, which is formic acid. For this molecule, this is a dissociative attachment reaction. Again, the scattering electron comes, sticks around the molecule for a while, and then the molecule breaks up in two fragments, and one of the fragments takes away the electron with it. And so I said, well, this is simple enough to study. I believe that what's going to happen here is we're going to get this shape resonance, and then the hydrogen is going to pop off. Well, I started doing this calculation. I realized that that was not the case. And what was puzzling about this is the following. Both the target molecule and the fragments are planar. And so I was doing these calculations expecting to have the intermediate state, this transient state, to be planar as well. However, after much trial and error, I realized that if I pulled these oxygen atoms and then I took the hydrogen out of plane, that enabled this hydrogen to pop off, right? So we had to go beyond what was intuitive for us, which was to keep everything planar. So this is just one pathway I found for this phenomenon to occur. There could be many more, right? And so this is where creativity comes into place. This is open to creativity because what we discovered by doing this is that there are intrinsically polyatomic dissociation dynamics here. Some sort of a hidden dynamic, except that it's not hidden to us at least, because we need to understand how these dynamics occur. But even in a simple small molecule like this, we can see that we cannot use the simple 1D models that have been used until present time, because the reality of it is much more complex than we imagined. Now I'm going to briefly tell you about the biological physics that I've been doing in the Department of Physics at UC Davis. Here you see a list of neurodegenerative diseases with associated proteins. There are several similarities between these diseases, and shedding light on one may well be very informative to understanding other diseases as well. So I'm going to focus on the Prion protein, which is a protein we studied more deeply at UC Davis, which is the one associated with the Crutchfield-Jakob disease. That's a human version of the mad cow disease. So before I do so, though, because I know that this is a very general audience, I put together this slide to explain what proteins and how proteins are constructed. Well, pretty much having Italian blood in me, I need my hands, and so this is difficult, this is challenging for me to use this microphone right now. But can you hear me if I speak loudly? Excellent. So, how are proteins formed? We have amino acids. Amino acids are the building blocks of proteins, right? And so, but what is an amino acid? An amino acid is a simple structure. It's a chemical structure that looks pretty much like this, right? It has a central carbon here, which we call the alpha carbon. It has an amine group sticking out from one side, a carboxyl group on the other side. It has a hydrogen atom here, and this R here represents a chain of atoms. It could be as simple as a single hydrogen. It could be a whole chain, a more complex chain. The only difference between one amino acid and the next is this R, this chain here. So how do they get together to form proteins? Well, they undergo what is called a dehydration reaction because they liberate a molecule of water in the process. This carboxyl group combines with the amine group, and then they form a chain. Now, this here is a protein. We have a chain of amino acids, we have a protein, right? But the protein is not a nice layout, straight structure in space. Instead, it folds up, it curls up in space, and they form structures, which are called secondary structures, that could look like this strap that's looped around here. This is called a helix, or it could form sheet-like structures that could be parallel or anti-parallel. These are beta sheets, and I need this to, there are more, but these are the ones I need for the remainder of the talk. So what do we know about the prion protein? What we know is its primary structure. Each letter here represents one amino acid, this one letter code here. We know part of its secondary structure. We know it has two beta sheets. We know it has alpha helices, the ones represented here and up here. We also know that they bind to copper. Now, why is this binding of copper even important? Well, because it is believed that it is the breakdown of metal homeostasis, of metal equilibrium, which is a key factor in many of these neurodegenerative diseases, right? And so there is much debate whether binding copper is going to be neuroprotective or neurodegenerative, meaning whether it's going to trigger the disease or it's going to inhibit the disease. So this motivated the study, and what have we found at UC Davis? Well, something everybody needs to know is that everybody has prion protein in the brain, yes? We all have prion proteins. If you're not sick, it means you have a healthy form of the prion protein, right? Now, the only difference between healthy prion protein and diseased prion protein is its conformation. It's the way it folds up in space, right? So over here, we have a representation of what healthy prion protein looks like, the way it folds up in space. This is what diseased prion protein looks like. Now, what we found at UC Davis is that if you look at these two binding motifs of copper, in order to bind copper, the prion protein needs to bend around the copper. It needs to acquire a bent structure that is not consistent with the straight structure that you see here that is necessary for this diseased form of prion protein. So that's an indicator that binding copper can be neuroprotective. Now, I have studied segments that are known experimentally not to bind copper. So I've studied the binding properties of copper in these segments. The fact that they do not bind copper experimentally is not surprising. Why is that? Because of the because those segments I'm studying are within this alpha structure, right? Alpha helical structure. However, if this alpha helices are disrupted, for instance, by lowering the pH of the environment, that is something that could happen during neuron synapses, for instance. At that stage, then, it is possible for this to bind copper and therefore follow a path that's different than refolding into the disease structure. So that was a little bit the motivation of studying this. What did I do? Well, I constructed a candidate structure, and I studied I made an estimate of the energy of binding. And with a very simple model, right? I have the energy of, I'd say the energy of binding is the energy of a complex, which is the whole thing, minus the energy of the fragments, yeah? Here's the copper and some water molecules coordinating that, and here's the rest of the prion. So, when I started running calculations here, the typical calculations that one runs is calculations for these large biomolecules, and it found that even within those fragments that are experimentally known to bind copper, molecular dynamic simulations do not reflect that. Okay, and there are reasons for that to happen, because you need to use more approximate methods than in order to describe these huge molecules. If I do quantum mechanical calculations on these proteins, the energy of binding is physically large. And there are reasons for this as well. I don't want to get too technical here. But what I came up with is say, okay, I'm going to embed quantum mechanical calculations within the molecular dynamic simulations and see what happens then. And what happened then, and I'm going to skip this because of lack of time, what happened there then is that we found that the energy of binding of these fragments are within reason, and they're even larger than the binding of fragments that are measured experimentally to bind copper. And so I ran other tests as well to measure the affinity of different metals, and those follow experimental trends. There are many unresolved issues, so there's lots of room to create and to contribute in